of the 2024 HFIP annual meeting. We're going to go ahead and get started. I apologize for the early start, but we had a couple of sessions we had to squeeze in today. So we actually start 15 minutes earlier than we have been and end 15 minutes later. So hooray, this is your problem day of long stuff. First up session is our hurricane observation session. It's chaired by Renee, who you can't see on camera, but in the room you can see her waving, and June. And I will send it over to them.
Thanks, Aaron. Yeah, it's a big thanks to my co-chair, June, for helping. And also Jason, who's about to, okay, well, let me move over here. And also big thanks to Jason here. And I think Lisa Bucci is also here for putting together this session. We're really excited today. So I won't take any more time. I'll pass it over to Jason to talk about the Hurricane Field Program.
It's working. Okay, fantastic. Okay, thanks, guys. So I am here to present on APEX, otherwise known as the Hurricane Field Program, on behalf of Jason Dunyan. He's the director. I'm the deputy director right now. He is bogged down in proposal writing and other business. He's going on leave next week. So I'm in charge of everything next week if we have a system. Hopefully that doesn't pan out as it's looked. So I'm going to give an overview of what HFP has looked like, not just from the observation standpoint and the science, but how it operates. So I'll start with our goals and logistics, go into the science, the observation strategies and impacts, and then really hit on the challenges as well. One of the big challenges is balancing research and operations. This has become more of a conversation lately, and it's worth talking about here. And then finally, offer some concluding thoughts. Our goals are pretty simple. We collect observations that span the life cycle of the tropical cyclone. We're interested in anything from genesis to the end of the TC. We also develop measurement strategies and technologies. A big one right now, for example, is UXS. Joe Sione's going to talk a lot about that a few talks from now. We also are very involved in uncovering issues with instruments. For example, Zoran is going to talk about SFMR issues. This is all very critical developments under what APEX is doing. Finally, we are also very interested in improving understanding of physical processes. I'll talk a little bit about all of these goals throughout this presentation. We have a lot of great partnerships throughout NOAA and also really across the nation. The collaborations nationwide are really focused on the ocean side. For example, ONR Magpie, NOAA GOMO, University of Washington and Scripps. A lot of that has to do with expendables, but we have a lot of great collaborations nationwide. In terms of logistics, you can see our operating ranges for both the P3 on the left and the G4 on the right. We cover most of the Atlantic basin, focus really on the areas nearer to land, the Southwest Atlantic, the Gulf, and the Caribbean, but we can operate out of Cabo Verde. We did not do this year, but we have done it in the past. Here is what we actually did this year. You can see we covered just about every square inch of the Gulf. You know, there's been a lot of activity this year in the Gulf, a lot of landfalls, and so that's where we focused, but we did have some out in the MDR as well. We had Beryl early on, then a non-developing wave and Ernesto. Good coverage out there as well. We flew 7, 8 TCs. We flew a number of TCs, I think 8, in addition to the AEW. Here's a summary of the year. Here, there we go. 8 tropical cyclones. A lot of different research modules, 12 with all our different collaborators. 49 P3 missions. If that's tied for second most that we've had in the history of the field program. So if we get one with this system coming up, that would be the second most. Also 18 G4, that's nothing to sneeze at either. Over 1,400 drop-ons processed, a bunch of AXBTs and other expendables, 190 TDR analyses transmitted to EMC and NHC. Those are extremely valuable, not only for situational awareness, but also they go into the models. A lot of this data goes into the models. Talk about that in a little bit. So in terms of the schedule, this is our formal schedule, but it's a lot more than just what you see here listed. We have our meetings starting at 9 a.m. and going throughout the morning. Then, of course, we have our HRD map discussion. But behind the scenes, there's a lot going on. Text messages, emails, G-chats flying, starting, sometimes before 7 a.m. There's a lot that goes into the flight planning. There's a lot that goes into the expendable planning. Here we have on the right, a flight planning kind of zoom in that Jason Dunyan is so well known for. These actually go on the P3s. They help the flight directors figure out what we're doing. And it takes a lot of work to try to figure out, for example, when UAS are involved, from safety considerations, where they're being dropped, make sure everybody's on the same page. But also there are other assets involving sail drones and other expendables. We all want to be on the same page on how all these are used and allocated, and AOC needs to know that it all makes sense from their standpoint as well, and from a science standpoint. So we got that going on, and they also have the crewing. We've focused a lot more on ground-based crewing in the most recent years, and that takes a lot of scheduling. So we have, of course, the people on the plane, but we also have ground crewing, and that's an example of a crewing schedule from Milton. We have planned all this out, as the storm goes on, we're filling in slots, making sure all the slots are covered. I'll talk a little bit more about that towards the end of the presentation. So moving on to the science, we have a lot of unique observations. These are all TDR missions, at least from the P3, so it makes sense to start there because that's the core of what we do. Airborne radar is really unique. Nobody else can offer it, and it is critical, is being processed by AOML scientists, and the data, as I said, is sent out to EMC. The radios are sent out to EMC, and the analyses are sent to the Hurricane Center. They're great. Specialists love them because they can help give, an undercover look of, or under the hood look of what's going on in the storm. How is the tilt evolving, for example. They also, on the science side, really provide context for other wind measurements. They help us understand, what our other observations are telling us. And they're also used scientifically to help understand intensification. One, thing that's been explored recently in the science community is how tilt evolution relates to intensification. And the TDR data has really been very important for that. And here we have an example of Idalia where the low and mid-level centers aligned prior to rapid intensification. You can see the L's and the M's on this diagram here. These are TDR analyses, and they align as the storm is intensifying. So that data is really valuable for understanding those kinds of processes. Of course, it's more than just TDR data. We have a lot of unique observations on the NOAA planes. We have cloud physics, for example, on N43. We have radial occupation instruments on the G4 as well as N43, a W-band radar for looking at really small, very small particles, very cloud particles, aerosols. I have leftover slides at the end where we can, if you have questions about what these instruments are actually looking at, there's more information. IRAP has been critical for understanding what's going on with SFMR. Zorana is going to talk about that, I think, the next talk. We also have instruments that look at wave properties on both N42 and N43. In terms of the modules, so as I said, we go from Genesis all the way through in-stage, also ocean observing and satellite validation. I'm just going to hit on a few of the modules that we use this year, not all of them, just a few of them to give some highlights. So start with the early stage spiral stratiform module. So we literally do spirals from the low levels up through 25,000 feet or so to look at microphysical properties through the freezing level, to understand what's going on in terms of the microphysical structure of the storm. How is it evolving? What's going on in that stratiform region? That was used in Barrow Ernesto. We also use a vortex alignment module where we have we try to align one of the legs of this would be a typical butterfly pattern on the right, and we align one of the legs such that we fly through the axis of the low and middle level centers and then fly back, and we're trying to understand the alignment process. So this would be early on in the TC. That was used in a number of our TCs this year. On the left here, we have the eye-wall mixing module. So this is mature stage. So one way that we look at eye-wall mixing is drop a rapid series of dropsons and look at spatially how the structures, the thermodynamic and dynamic structures vary over a very short distances at that interface. So that was used in our mature storms, Beryl, Helene, and Milton this year. And then UXS, Joe's going to give a talk on this in a few talks from now, the Rico Suave emerging tech. Of course, there's the drones, but we also have instruments like streamsons That was used prolifically this year. It's been, I think, the biggest UXS year so far that we've had. So that's been a tremendous success, and we're very proud of it. We also, as I mentioned, have a lot to do with ocean observing. And this is kind of the frontier, right? We have a lot left to understand about the atmosphere-ocean interface. And this graphic has made it around quite a bit, and it's for good reasons. It's a fantastic graphic. And it just illustrates how we're working with all these different platforms, from the plane, the drones, and the undersea, like the gliders, the floats, drifters, and then right at the surface, the sail drones. We work to coordinate all these observations so that we get a view of what's going on from the atmosphere down to the ocean surface, and then underneath too, because this is going to be really important for the next stage of coupled modeling and coupled data assimilation as well. So we've hit on this the most, really, out of all the modules this year. This was done in every storm so far. So these observations have great impacts. We're doing all this science. We have all these modules, but there is an end to this, right? And I'm just going to hit on a few of the impacts. One of them is R&D. And since this is HFIP, why not talk about HWRF, right? One of our great successes from HFIP. The AFEX observations were really critical in the development of the HWRF physics. This graphic here demonstrates, on the left, a drop-zone composite of the radial inflow into TCs as a function of the RMW and the height up to about 2 kilometers. On the right, you have different iterations of HWRF started in 2011. And you can see the early versions of HWRF, the physics was poor. The boundary layer was far too deep, and that caused problems. It caused problems in the inner core structure in particular. It wasn't able to resolve the hurricanes with fidelity, and that caused forecast issues. So with these observations, we were able to correct HWRF and make it better. And you can see as time evolved through 2018 and 19 on the right, the structures became a lot more representative of what was seen in the drop zones, and thus the forecasts also got a lot better. June's got a whole talk on this, a few talks from now. This is just one example, but there's a lot more on how our observations have been used on the model R&D side. So it's really exciting to see the observations put to work in this context. Of course, there's also other benefits, more immediate than model development. And one of the ones that has gained a lot of visibility is the model impacts, the DA impacts and the forecast impacts. So here is an example from Hurricane Ian of all the data that got into one cycle. This is early on in the storm. And the blues and greens are TDR observations. You can see they dominate the spatial structure of the observations being assimilated in the inner core. And there's also others. There's SONS and flight level OBS as well. These OBS have a tremendous impact on the forecast, especially early on. Gus showed this graphic on the right. This is just one example. Me or Sarah or other people have done dozens of talks on the impact of these observations. In HAFS, we looked at the net impact of the reconnaissance, and this is for tropical storms in the 2023 season. The data improved the forecast by about 20%, the intensity anywhere from 20 to 40%. So this is fantastic. It has gained a lot of visibility, and NHC is excited about it. They're using the planes a lot more, and it's all good, but it does introduce some challenges. And one of these challenges is this is a graph that shows back from the very beginning the number of P3 flights in blue and storms in red that we've flown per year. And it's not quite a hockey stick, but you see towards the end of the last few years what's going on. We had the first TDR missions where we began transmitting the TDR data back in 2013. That's that blue star. And what happened since then? All of a sudden, we have a lot more flights. Those are, in the neighborhood of 40. You can see 40 there. That was a number that wasn't frequently hit in earlier years, and now we're hitting it pretty routinely. 49 this year, as I said. So that is a challenge from HRD's perspective because we're still on the hook for processing a lot of the data and doing all the things that I talked about at the beginning of this presentation. And here's a sample of our 2024 what HRD has been doing for this season, the big challenge. We've almost 3,000 hours, person hours, dedicated to these missions, in terms of processing data, getting the data out to the GTS and to the Hurricane Center, getting the flight planning, crewing, all these things, that it all adds up. And 90% of those have been related to operational missions. Actually, 70% have been ground-based. That is something new that has evolved in the past few years. We definitely did not have that much ground-based support in the past. Why this is such a challenge is because HRD isn't very big. We have 10 people contributing to 80% of these hours. I was one of the high contributors. Gus did a lot. Jason Dunyan had over 500 hours. So that is extremely challenging. And then there's the cost, which about 300,000 this past year. We don't have a huge budget, so 300,000 is a big chunk of our budget, right? We have mitigations. The ground-based support has helped. We don't have to pay for travel as much, not as much onboard support. The flights are grueling, right? So it definitely cuts down on that, but you're still paying people to process SONs. Automating the TDR workflow, once that is automated in the future, that's going to help a lot. And so that's something we're working towards. And then we're also working with OMAO and the Weather Service on operational transition of these missions. Concluding thoughts. So what is our goal? Well, we want to continue partnership to maximize outcomes. We want to partner with the Weather Service to maximize outcomes, continue with joint missions when we need to, but we also want to have missions that are just NWS tasked, right? That we don't necessarily have to be on. And then we also have missions that are important for us to do on our own that aren't necessarily tied to operations. So this will enable HRD to maximize its effectiveness at generating, at addressing next generation science needs. So in conclusion, we collect really unique observations. Nowhere else in the world can we get this data. They span the whole TC lifecycle. Our operations are evolving, though, in the face of budget and staffing challenges. This is just honest truth. So in the apex of the future, it's going to look a little different. We're still going to be gathering data on operational missions, but HRD is going to have a smaller footprint. But overall, this is good for everybody because it's going to allow HRD to focus on what it does best, like the next generation instruments, like airborne radar. What are we going to do next for airborne radar? And other instruments, what are we going to put on the new C-130? So this is it. That's all I got. One last slide. You can scan the QR code to get to our data page, but I'm probably at 15 minutes by now, so we'll end there.
Thanks again, Jason. This was an excellent talk to kind of lead into the remainder of our talks within this session. And this next one that Jason alluded to a few times will be by Zorana Jelinek. She's going to have kind of a double header. Zorana has about 30 minutes to talk to us about SFMR as well as IRAP. So we're going to get set up really quick and then get going. And also, like all other sessions, please keep your Q&A to the end. We have a Q&A session of about 15 minutes right at the end.
Okay. Good morning, everyone. Today I'm going to talk about two instruments that have been flying together for almost 20 years, but had very different stages of development. And it's only through the funding from WPO that we started merging them together. And what this funding also allowed NASDIS and HRD team to start working more closely together. And you can see that results that we have now through that partnership are much, much better than we ever had from this analysis before. Now, while this talk is going to show one of the best detective works that we have ever done, this is one of the hardest talks I need to give. What I want to talk first about is, why is this not moving now? Oh, I don't know. Okay. I want to start with the IRAP because I think a little is understood what the IRAP impact was through the history of these measurements. We learned about IRAP since we started producing near real-time data, but as I said, IRAP has been flowing for 20 years now. It's the instrument that was developed through 6 PhD and master theses from UMass with the NASD's help. And through the years, the IRAP impacted every single operational scatterometer product that you are using in daily operations, because we used it to calibrate and validate high wind retrievals and improve products. Those products have been used in operations by forecasters, used in the numerical weather prediction models, because we do fly it in winter in extratropical cyclones. They were used to develop new insights in the physics of extratropical cyclones. We also used IRAP to test new technologies. So IRAP is going to impact the next generation scatterometer that you are going to use, because we have flown for 6 years antenna that's going to be on the next generation ESA scatterometer that is replacement for ASCAT. By flying that antenna, we were measuring the cross-pole radar signal which then influenced the SAR GMF that you are using today in operations as well. And then since 2021, we started producing near real-time products from IRAP and looking at IRAP in connections with the other measurements, and that's what I will concentrate today. So what I want to say, thinking of the Wallace's funnel, while IRAP has been sitting in that funnel for a while, it's been impacting so many things that went through that funnel that I think it's already did a great service to the operations. What I want to see coming out of that funnel is not necessarily IRAP to operations. We want to see next generation wind instruments from the aircraft that will be influenced by these measurements. Now, as I said, we've been producing near real-time IRAP data in the last 4 years. And the first year was early development. We were happy just to be able to produce the near real-time product, right? Then when we first did that, we started realizing what we are missing. So we were updating the hardware, updating the software to get better measurements. Last year, we were acquiring measurements from 8 different channels in order to understand what are the best type of combinations that will give us the most sensitivity. And this year, I can say we are in early application stage where we are producing near real-time winds. And we can only do that from 2 channels, but in research mode, we are producing the winds from all air channels, blending them, and then producing one unified product. So talking about blending, this is an example. I think this was Milton. You can see 3 channels here, 2 from KU band, 1 inner angle, 1 outer angle, and then C band in the strongest rain. C-band has the best sensitivity, so when we blend them, we get these profiles. And you can see here, this is 60 kilometers of profiles that we have, wind profiles that we have every 150 meters. So that's almost like 350 sondes along this track. What we learned is that next generation profiler should operate on at least 2 different frequencies, ideally 1 non-attenuated. Choice of incidence angle is important, and I'll show you why on the next slide, and narrow beams are critical. Now, the reason we can, sorry, I can't see.
There's a little box.
Oh, no, everything's. Okay, so the uniqueness of HFIP it's in its acquisition system that allows us basically to look at the power spectrum all the way through the surface. And in this movie, you saw as the IREP is rotating antenna, you see the rain signal, which is that column going from top to the bottom, and the surface signal going in and out from each other. What TDR cannot do and other radars, so far they could not separate the surface from the rain. That's what we are able to do with IREP, and that's why we can get the winds in the lowest boundary layer. Now, this year, we were blending the lowest 3D Doppler wind estimates with the IREP winds from scatterometry. The problem is that in this intermediate rain region where we have low sensitivity from Doppler and then attenuation from scatterometry, we are missing wind. So that's next thing that we need to work on to populate the track better. The other thing that that is very interesting to work on, I'm concentrating now on different applications that I see are very needed from, and that can be derived from these measurements, is understanding the impact on rain on radars like SAR or ASCAT. Because we have this spectral processing and we can separate rain and surface, we can actually understand what is the attenuation part of the rain on the backscatter signal and what is the volume backscatter. We can implement that in SAR and ASCAT processor and get better retrievals from satellites. We also have an excellent opportunity now to re-examine WL150 algorithm that's been used on sondes forever. As I said, when you look just at these two passes through Milton, we have like almost 600 profiles that we can compare with the sondes. For these two particular passes, we had one sonde that worked and one that quit. What we could do then, look at the histogram of the profiles. So basically going towards the mean profiles that were before derived from sonde and comparing that original profiles from Franklin 2003 to what we are seeing from IREP. And you can see how different they are. We are also working to support IREP data assimilation. We have created the files specifically for data assimilation experiments that are lower resolution. We created 3 different files and also created derived winds from it to for data assimilation to be able to take it basically the similar way that they are assimilating TDR. Now, let's talk about Milton intensity. What I'm showing here is time series of the flight level, which is blue, SFMR, which is black, and the estimates from 3D winds in the rain columns closest to the surface, which are green. And you can see that SFMR is highest than the flight level is definitely higher than IREP. And the question is, which one is correct here? Now, to answer that, you really need to see what's happening in the column. And if we look at two profiles that are above where the SFMR had the highest winds, you can definitely see that the column winds do not support those strongest winds. So this summer, we took a lot of time to understand what's going on with the SFMR. Part of the WPO proposal was to document the errors in the SFMR. And initially, Heather and I started with the assumption that the main sources of error are basically within the forward model, because probably the surface emissivity and rain transmissivity models are not adequate. So utilizing IRAP data, we developed, and this was using actually 2 flights, with the one SFMR that was behaving properly. And we developed the new transmissivity model. And then I'm going to show you results in this flight through Ian, where we have the wind speed drop-off, drastic wind speed drop-off that we noticed is happening quite often in the SFMI retrievals. Usually we talk about the overestimation, but the truth is we have both over and underestimation. As you can see from the profile above, there is nothing in the profile that even remotely suggests that winds should be this low. Now, if we implement our new transmissivity and plot the new wind speed, you can see that we are starting getting something that makes more sense. It's not that we are just getting higher winds. What we notice is also that the peak of the SFMR winds is shifting. We notice that a lot, that IRAP is suggesting that maximum winds are within the rain column, but very often SFMR shifted outside from it. So part of it is this transmissivity model. The other thing we noticed too is that if we look at the retrievals within the SFMR algorithm, the operational algorithm weights all the channels the same. So we decided to run this experiment where we produce the ensemble of solutions weighting the frequencies differently. And you can see the IRAP is the green line, or pink for rain, that we do have. If we weight solutions, frequencies differently, we do get to solutions that are closer to IRAP. That made us think, okay, it's something with the inversion algorithm that we need to fix. And we thought we were done there. But then the season, and I was ready to start writing kind of manuscript for the paper, but I was like, okay, let's just see how the season starts. And then the floodgate opened. So season started early. We barely had IRAP on. This is first flight in Beryl. The AOC installed the unit 2 on 42 with IRAP, and we look at the comparison, and you can see scatter plot has some bias that is a function of the wind speed, actually. During that flight, the HDOPS data was really bad, so they decided something's wrong with this instrument. What I'm showing are the actual raw retrievals, not the HDOPS data. So they decided to switch to unit 1. When they switched, and then we look at the performance with IRAP, we see it's different, right? Now we have this kind of 5 meters per second bias, and we have some bifurcation there. Okay, we are thinking at this point is the calibration. Finally, they switched to unit 3. AOC owns 3 units, and this is the result we got. Okay, so at this point, we are still thinking, okay, it's calibration. We can do something about it. So we asked AOC to help us recalibrate. And we designed this experiment when we were ferrying back from Ernesto flights. We have flown over 2 ASCAT SWATs. We reproduced ASCAT to high resolution. We checked both IRAP and SFMR, and ASCAT perfectly agreed with IRAP, but didn't agree with SFMR. We recalibrated SFMR and we got better solutions. You can see on the time series plot, the green and black are IRAP and ASCAT. The red is original SFMR, and the blue is recalibrated SFMR. So at this point, we are thinking, okay, we know what to do. Let's try do that for other AOC units and recalibrate them. So we designed the flight on September 5th. There was no storm, it's calm wind. Again, over the ASCAT passes. The red is, what is red here? Flight level. The green is KU band, ocean surface vector wind retrievals. The dots, red dots are zones. And the colored line, black line is ASCAT. And you can again, and then yellow is the SFMR wind and the bottom SFMR rain rate. You can see SFMR is going plus minus 20 meters per second. Like what is going on here, right? And then first, we have a rain, there was no rain whatsoever, right, during this flight. So we look at the frequencies. Now, what you are seeing, the frequencies are being spread, the order of frequencies is wrong. And then they started converging together. So something's not right here, right? But what's not right? We looked at all the system variables, and what we figured out when we simulated brightness temperatures using IRAP winds or ASCAT winds, we noticed that there is the frequency drift due to change in the system temperature. So now we discovered the fourth source of error, which is frequency drift. But how often does that happen? Why did it happen here? Is it going to continue to happen? Right, we don't know. There is 20-something SFMR units. Okay, where do we go from here? We then said, okay, we recalibrated unit 3. Let's switch now back to unit 3 and fly the rest of the season with this unit and IRAP, thinking it's recalibrated, right? This is one flight in Helene. Comparison between SFMR and IRAP, what do we see is a bifurcation again. So where is that coming from? Next flight is from Helene. Now look at this. Now we have 5 meters per second kind of constant error. What is this, right? Then in Milton, we have almost like great agreement. So what does this mean? We have the same unit. Something's wrong with either IRAP or the SFMR, right? And believe me, I was pushing everybody to look at every single detail of IRAP because I wanted to be wrong. What we are dealing here is 20 years database of most extreme winds that's in jeopardy. I want to be wrong, but unfortunately I'm not. What we discovered is again that the bias varies with the temperature of the system. Bias also varies with time. So we looked, okay, why is this happening? So let's look into how brightness temperatures are calculated. The A coefficients are calibration coefficients that are derived every year for every single unit. The environmental information is contained in this variable gamma that are ratio of the counts of warm and cold load, differences with antenna load. There is warm and cold load there to be the near real-time calibration for the SFMR system. The small t's are thermistors, the actual physical temperatures of the system. Now, to look at the impact of only these two terms that contain gamma, we define this gamma index, and then we plot that for the constant set of temperatures for different channels, right? And this is for unit 1. And you see this kind of like umbrella shape because we debias brightness temperatures with the mean brightness temperature. And what we noticed is these discontinuities for the highest frequency channels. So the question is like, okay, what is going on there? The high frequency channels are the most sensitive in wind and rain. If something's wrong with them, that's where we are going to have problems in retrievals. So this was for unit 1. Then we were like, okay, how does this look? Oh my God.
We have about
I want to
7
show
minutes
the.
remaining, Serana. About 7 minutes.
Okay. I want to show this movie because we did this for every single unit. And what you should see, if everything is well calibrated, right? What you should see that this picture, when I play movie, doesn't change. I don't know. So look at this. These are all different units. What does that mean? If all of them are measuring the same scene, you are going to get different results. How can you trust any of these units? Now, but why do we have these breaks, right? We dig further. What we found out is that, again, the SFMR has a cold load and warm load that are used as a real-time calibration of the system, and you want system to be linear. What we are showing here is the brightness temperature versus SFMR counts. The red is warm load, the blue is cold load, and the black are antenna counts. And you want to see this linearity, and we do see it. But what do we see for high frequency channels? You see that blue dot is in between black dots. What does that mean? Is that cold load counts are higher than antenna counts, and at some point they are similar to antenna counts. Okay, does it matter if the system is linear? When we look at the brightness temperature equation again, what do we see? In gamma, if the cold load is close to antenna, that means that gamma is 1. If gamma is 1, we are calculating brightness temperature just from system temperature. There is no environmental information in it whatsoever. And this happens depending on calibration. This will happen at different points for all different SFMRs. Now, then we decided to look, okay, let's check the intercalibration of the units. We use the unit 3 as a benchmark. You calculate the brightness temperature for all of them for each channel, subtract the brightness temperature of the unit 3, plot that as a function of gamma. These all lines should be on top of each other. This is channel 0, channel 1, channel 2, channel 3, channel 4, channel 5. So what did we discover? We discovered 7 sources from the SFMR. We discovered that all of them will be different. We did inform NHC and EMC during the season. The data simulation in HAFS has stopped. They did the study, and they have shown that bias in the surface pressure and Vmax got worse when SFMR was assimilated. The data still continued flowing from the Air Force, but by all means, this should not have been used for any decision making or in any research. That needs to stop. We calibrated all high winds using in satellites using the SFMR. We are using the machine learning and using SFMR as a truth in it. What is coming up? Something needs to be done about this. As I said, this is the most mortifying talk that I have to give, but one of the best detective works we have ever done. Thank you.
Thank you so much, Sarana. Again, a very sobering talk, but very much well needed. And we figured this community would very much benefit from hearing Sarana's detective work. So again, please keep your questions for the Q&A session at the end of our session. Thanks again to you, Sarana. We're going to switch gears a little bit and move over to our presenter, Lev Looney, who is going to be talking about ocean observations. As Jason alluded to, this is our next frontier, so another exciting talk. Over to you.
Look it online. Sweet. Awesome. Good morning, everybody. My name is Lev Looney. I'm a grad student at the University of Miami, but also working with NOAA AOML, specifically on how we best observe the ocean beneath TCs. And so I was honored to be asked to give this talk today, but I want to note that I think I'm the only one giving a talk about the ocean, specifically on the ocean in terms of observations. So kind of big shoes to fill. So hopefully I start to fill those. So how do we best observe the ocean in extremes? This presentation, even though the title is specific to AOML PhD, the work that I'm about to show is due to the work of many people and various groups and partners. So what's the ocean look like in these extreme environments? This is a video taken from a sail drone in Hurricane Fiona last year, and you can see it's pretty rough. It's extreme. Not the easiest place to observe. If you actually measure out these wave heights, the significant wave height was about 50 feet. The single greatest wave we observed in the storm was over 90 feet. Not easy place to observe. And so kind of stealing a little bit of the idea that Wallace gave the other day, I took to waiting way too last minute to make this presentation, and I went to AI. And specifically, I started with Google Gemini, which is Google's version of ChatGPT. And I asked a very simple question. How do we observe the ocean beneath tropical cyclones or hurricanes? And give it a short answer. I tried it without putting in how long the answer should be, and it gave me like a 10-page paper. So what did AI give me? Kind of like the first sentence a lot, the USA utilizes a multifaceted approach to observe the ocean below hurricanes, combining advanced technology and innovative research. It then goes on to talk about uncrewed systems and more conventional methods, such as data from aircraft, moorings, and whatnot. So I like that answer. I thought it was a pretty good answer. I like the idea of multifaceted. So looking at how we best observe the ocean as a whole, looking in the past 45 days for global ocean observations, we've used over 8,500 different platforms. So multifaceted, I think so. Over 20 million observations of the ocean over just the past 45 days. This is in a global sense. Over 2 million sea surface temperature measurements, over 1 million air temperature measurements at the surface, over 1 million sea level pressure, over 1 million surface wind measurements, over 600,000 dew point or relative humidity measurements, and over 350,000 wave measurements. But this isn't a talk focused just on global ocean observations. It's specific to hurricanes. So I switched back to AI, and I asked a question. Do we need uncoupled models for hurricane forecasting? Give it to me short. And what did I switch to ChatGPT because I switched computers, and Gemini wouldn't work on the computer I switched to. But they said, you really need coupled models for forecasting. It really helps for environments where everything is interacting. So then I went on further and asked an additional question. What about data assimilation? Do you need coupled data assimilation? So I don't take responsibility if everyone doesn't believe exactly what ChatGPT says. But the answer is yes, you really could benefit from coupled data assimilation for models for hurricane forecasting. And then I asked one last question. Then I learned I need to get off ChatGPT because it's very easy to spend way too much time on it, asking way too many questions. But it is an awesome resource. So I asked for data assimilation and coupled models, do you need coupled observations? And probably unsurprisingly, yes, you do. And Hyun Suk, I think, made a quote to me a while back that said, how can you look at coupled data assimilation if you don't have coupled observations? And so that's kind of what I'm going to talk about. How do we observe the ocean and the atmosphere together? So a lot of people have shown this figure. This is a slightly updated version, getting rid of some of the company names and emphasizing the variety. So across the board, we have things, as Jason hinted at, in the atmosphere from aircraft and aerial drones and drop-ons to below the surface with gliders, floats, and at the surface with buoys and drifters and even uncrewed surface vehicles. And so part of the goal is not just to take these as a whole, but put them together and get these coupled observations. And this is part of an experiment run by NOAA GOMO, or the Global Ocean Monitoring and Observing Program, called CHAOS. It's part of their Extreme Events Program. And CHAOS is the Coordinated Hurricane Atmosphere Ocean Sampling. And you can see the partner list on the right. There's over 20 partners involved. This takes a lot of work, and there's a lot of different people trying to get something together in extreme environments. So we designed an experiment for the Hurricane Field Program, and the goal was simple. Make this image on the left a reality. One of the most simple flight patterns is on the right. Can we just slightly adjust the flight pattern to fly over ocean observing platforms without changing or reducing any of the operational benefits? We also went a little further and designed some additional flight patterns, including those of dropping wave drifters and flying with uncrewed aerial vehicles, like the SUAS. And so how do we do? I'm going to show an animation of the observing platforms for Hurricane Milton. When I push play, you'll see the storm kind of go on and a bunch of different observing platforms. I want you to think about, how do we do? What did we get? What did we miss? What's needed? So you can see the P3 flying around. You can see the drop signs. You can see a mooring. I'll note we don't have any of the AXBTs in the animation. You can see the G4 as it continues around. Milton becomes a very pretty storm from satellites. But you notice early on, not much in the ocean. Now you can see a couple wave drifters that have been deployed. One of the SUAS, the Black Swift, flying around. You can see some more of the wave drifters starting to come up. And as we get closer to the coast, you can see a lot more moorings. You can see a sail drone. Some of these, I'm going to try to pause it right here. You can see the P3 flying around. You can see the sail drones here. You can see these are all wave buoys, as well as the spotter wave buoys, and even a glider. So starting to get a lot of observations as we get closer to the coast. I'll keep it going. And especially right on that West Florida shelf, there's a good number of ocean observations, but not that many well before it reached the shelf. So I'm going to break this figure down a little bit further. I'm going to start off talking about wave buoys and drifters. And so thanks, Dave Jones in the comments made a request that the figure should be updated to show wave buoys, and thankfully that has been done. And so how do we do? Looking at wave drifters, here on the right, granted these are not wave drifters, but it's sail drone wave measurements compared across two different sail drones in the Gulf of Mexico from Helene and Milton. Overall, in 2024, over 20 A-sized wave drifters were deployed, a majority from the NOAA P3, a few from the Air Force, as well as 50 full-size wave drifters as part of, I believe, a WPO-funded project along the coast. Many of these wave drifters, because a lot of them were in the Gulf of Mexico, ended up observing multiple storms. There's also part of the NOP program. There was multiple wave drifters and spotters deployed, and even part of University of Washington micro swifts, one of which was deployed in Hurricane Helene and measured over 13 meter significant wave heights prior to landfall. And somewhere like the West Florida coast, 13 meters is a huge wave to be dealing with. So that's wave drifters. What about below the surface? We've heard from a few different talks about the importance of getting below the surface. So gliders, these uncrewed, I call them submarine drones, but uncrewed underwater vehicles. So this is part of a project through IUS. They have the Hurricane Glider project, and the goal is simple: collect subsurface temperature and salinity observations and essential ocean features during hurricane season. By the numbers, this was the last update I had. By September 30th, there was almost 3,000 glider days and almost 70,000 glider profiles, over 60 glider deployments, and by then, 6 storms had been observed. Milton happened after September 30th, and then we had gliders in that. Over 10 days were spent with gliders, but in tropical storm conditions or beneath tropical storm conditions across 22 different intercepts. On the left, you can see that it's a partnership between NOAA and other partners, as well as the Navy. But again, gliders are fairly limited to the coast.
Yeah, we have
Oh.
5 minutes left.
5 minutes, thanks. Awesome. So there's a lot of profiles that we get. This is an example from Ernesto, from one of the gliders that was actually deployed very last minute off of Bermuda. another one of AOML PhD's gliders around Puerto Rico, as well as a Rutgers glider in Hurricane, it's supposed to say Beryl, but in Hurricane Beryl. Jumping quickly, we also had uncrewed surface vehicles. So these sail drones are used to measure conditions at the air-sea interface from the ocean, such as ocean temperature and salinity, ocean currents, but also at the surface with wind speeds, air temperature, and humidity. To get an idea of the size, you can see me standing next to one on the right. And so looking not including 2024, but in the past, how have we done? You can see kind of the general domain of where we've put these sail drones and where they've gone. And if we overlay tropical cyclones that we've intercepted, we're doing a pretty good job. I think there's been about 36 from 2021 to 2023 intercepts. In 2024, we've had 16 sail drone TC intercepts and 7 storms. We've measured for over 102 hours of sustained tropical storm force winds at roughly 3 meters. And we've been in about 14 National Hurricane Center citations. As you see here, I think one of the most impressive ones was in Hurricane Leslie, where we talked about the sail drone sea surface temperature was warmer than anything else that was there really wasn't much else in the area, but warmer than what was expected, and that could be a reason the storm intensified more. So some of these include Leslie, like I just mentioned. We also had ones from Milton and Ernesto, but this required a lot of work. With the 14, I kind of keep track of where they are so we can get a reference. But as many people at NHC knows, one of the problems is with all these new and upcoming and emerging technologies is getting the data to the eyes of the forecasters and to those that care. And so in 24 hours with Hurricanes Milton and Leslie, I sent 22 emails over to the National Hurricane Center. And it is one of the ways that we still get the data over there today. Hopefully that will change, but it is unfortunate that it requires so much work, but it is part of new technologies. And so bringing this back to coordination, this is a figure that I've created from 2023, just showing the mess of everything that we did within 100 kilometers of a sail drone. And so again, this is part of chaos, and it is a rather chaotic figure. There was a lot of coordination done. Jumping quickly to 2024, Jason showed actually this exact flight plan earlier for Hurricane Helene, but I liked it a lot because you can see a glider up in the top right, a sail drone. You can see the SUAS and wave drifters. There's been 84 days so far this year of glider sail drone coordination, 19 P3 sail drone flyovers, numerous P3 glider flyovers, numerous coordinated drop sondes with different ocean observing platforms, and a lot more, and it's still ongoing. And again, this required a lot of work. So the last thing I'll kind of end with is I created this last year for the sail drone team, we had a group text to help plan things out. And so I ran a number of texts per 24-hour period throughout the hurricane season. So there's over 4,000 texts sent, and what's interesting is if you pick out the peaks, you can pick out the storms. But you can also see a constant downtrend. After the first storm, everyone got kind of exhausted. What's also cool is you can do a time analysis and see what day of the week the texts were sent, and also what time of the day. Over 70% of the texts were sent outside work hours. As we all know, hurricanes don't work on a 9-to-5 basis. So it requires a lot of work. So with that, I'll stop now. I'll take any questions, and I'll leave one more video of what the ocean looked like in Hurricane Helene. I think we're doing questions at the end. So thanks.
Thank you so much, Lev. Excellent overview of what's going on the ocean front. We are going to move on to some observing systems through HRD with a particular focus on R2O efforts, presented by Jun Zhang, my co-chair.
Good morning. Thanks, Renee. Thank you all for coming to our section earlier, 15 minutes earlier than usual. Thank you. My name is Jun Zhang. I'm from AOML and CMERS. I'm going to give a quick update on our recent observation-based research and mostly R2O efforts for improving hurricane forecasts.
1 second, we're getting it
Oh,
online.
okay. Oh, sorry. Oh, changing computer.
Okay, you're good.
Okay. So you will run the slide, right? Okay. Oh, I already did the introduction, so next slide, please. Yeah. So here's the outline. So I will show one example of observation-based work, and then I'll, thanks to Jason Sippel, giving a nice introduction. So I will mostly focus on telling the history of how we use observations to improve model physics and also for model evaluation. Near the end, I'll show our current project funded by HFIP that focus on providing a wind gust prediction tool. Next slide. Oh. Okay. All right. So I'll just show one example in terms of understanding based on observations. This is the result from my paper using TDR profile data. So we composited 20-year Doppler radar data, profile data. The profile data has advantage of vertical resolution. It has a vertical resolution of 150 meters compared to the SWAS data that has 500 meters. So this is one of the result when we group the TDR data for storms focusing on the decay rate of tangential winds. So we look at the boundary structure in two types of hurricane vortex, the narrow vortex on the left and the broader vortex on the right. So you can see in terms of the maximum boundary inflow in the narrow vortex is actually located close to the radius of maximum wind, RMW, while in the broad vortex, the peak inflow is actually in the outer hull region. We also found that the intense updraft or convection is more concentrated near RMW in the narrow vortex, but it's broadly distributed in the kind of like in the broad vortex. And interestingly, we found that narrow vortex actually tends to intensify, while broader vortex tends to weaken or maintain steady states. So, and also we try to link our observations to theoretical work in terms of the boundary dynamic control, and also this new theoretical work in terms of ventilation. So basically, the boundary spin-up mechanism argues that when this, I don't know if it's working. So when this peak inflow is located near MW, that would transport a large absolute angular momentum that helps spin up the tangential wind. At the same time, we have stronger updrafts that helps ventilate mass out of the boundary layer. So that is a new concept of the theory. So that our observations kind of support that spin up our ventilation dynamics. Okay. So from now on, I'm going to talk about R2O. This is an observational section, but I'll talk a little bit about model physics. So this is just want to give you introduction in terms of boundary parameterization schemes. There, to my knowledge, there are two types of kind of PBL schemes. The first type is the additive safety-based scheme, and it's essentially the K-profile method from O'Brien 1970. So in this type of scheme, the flux is parameterized through additive safety. So there's a downgrading term, and then there's a non-local term. So in the HWRF, we use this type of scheme actually. So and then this is the EDMF scheme. MF means mass flux. So this is the latest version. So basically, it's tuning the entrainment process near the top of the boundary layer through mass flux or boundary layer height. So this is and also in HWRF, we try to tune this KM by adding a parameter in this equation. There's another type of scheme that's based on turbulent kinetic energy, the TKE scheme. This is a one half order turbulent closure scheme compared to the K-pro method is one first order turbulent closure. I took some equations from Jung-Gil Han's paper. He's from EMC. So just show some equations from TKE EDMF scheme. But the early version, the TKE type of scheme, like a Miller Amada or MMS scheme, is basically there's no mass flux. It's the kind of in that scheme, the effective additivity is parameterized using Nixon lens and the TKE, and also there's a dissipation term, etc. So this is the scheme become more complicated. So people added the mass flux components, and again, it's trying to kind of tune this the permutation of fluxes. So there are two types of schemes. So in HWRF, so we actually collaborating with EMC and other agencies and our AML folks. So we try to improve the HWRF PBL physics back to 2011, 2012, as Jason Siebel kind of hinted. So we try to use limited observations to tune the additive safety and to make it closer to observation. So basically, and we did a verification on the right-hand side of this. This is about 100 to 200 cases. We found that in terms of both the absolute error is significantly reduced. We also corrected the low bias of HWRF. So this work actually contributed to our gold medal. So that time we also won the MS Banner Miller actually for this work. And so we extended our knowledge based on our experience of tuning the HWRF model to our HAFS model physics improvement or evaluation. This is Andy's work working with me and Gobble. So this is back 2021. So we try to look at the distribution of vertical additive safety as a function of wind speed in different kind of schemes, but using the HAFS framework. So this EDMF, GFS, and TKE, those are the original scheme, and then you see the letter M, that means modified. So basically we just lower the original KM in those schemes, try to match observations. And you see the modified GFS and TKE scheme definitely are closer to observations. And also we look at some of the structural parameters. For instance, here we look at the surface inflow angle, comparing the modeled surface inflow angle to observations, job zone observations. You can see the modified PBL2 schemes did a better job than the unmodified. So, and then this is again Andy's work. So we run around 100 cases by comparing the unmodified EDMF scheme versus the modified EDMF TKE. This is not a clean comparison basically, because we're comparing two types of schemes. So, but just want to see, the modified TKE scheme did a better job for inflow angle. So we want to see how does it perform in terms of the intensity and track forecast. Actually, you see there's some small improvements in terms of track forecast, and in terms of the model bias for early forecast hours, it improved, but then the much higher large bias. So the result is kind of mixed. So the recently Xiaomin is here actually. So Xiaomin, a former postdoc from AML, so he did more modification to the FTKE scheme. So this is a clean experiment. So he compared the unmodified versus modified and running hundreds of cases. So he did 4 changes. He modified the coefficients in terms of the dissipation rate, and also to match surface layer and boundary layer. He reduced the mixing length to be close to the observation in my paper and the areas. He also modified the boundary height configuration. He also turned off this mass flux configuration for wind speed higher than 20 meters per second. And here's the result. Look at the right side first. You can see that definitely the intensity forecast is definitely significantly improved, especially for early forecast hours before 96 hours. But there's some small downgrades in terms of the track forecasts. He also looked at the surface inflow angle. You can see the in the modified TKE scheme, you see the peak inflow angle magnitude is improved, but the outer core region is kind of downgraded slightly. Yeah. So I mentioned about R2O, but we also did O2R. So based on all these physical improvements and evaluation tests, we better understand the physics too. So we found that when we lower this turbulent mixing strength, we see a much stronger inflow, and that's closer to the MW. That also is correlated with stronger updrafts in the IO region. So overall, the storm is stronger when we reduce the vertical diffusivity. That's why we kind of lowered the model bias by doing this. We also, I'll just quickly talk about other type of physics. There's also a horizontal diffusion in HWRF. So it's kind of the horizontal component of turbulent fluxes is also parameterized by eddy diffusivity, but it's horizontal diffusion, horizontal eddy diffusivity. And in HWRF, this horizontal diffusivity is linked to mixing length and also the model grid point. I mean, the model size, basically. So the delta here, the model size. So there's a tuning parameter also in this configuration. So what we did in the 2016 version of HWRF, working with Zhang, Vijay, and others from EMC. So we lowered the horizontal mixing length based on observations. It's kind of the paper I did with Michael Montgomery. So this is the verification. So Zach run 200 cases for us, working with SIPO. So you see, this is the forecast score. So compared to 2014 version HWRF, you see the both 15 and 14 version did better than 15 and 16 version did better than 14 version. But when we lower the horizontal mixing length, we improve the intensity by about 10%. We also reduced the bias significantly. We also did a verification in terms of storm size. So the storm size is significantly improved in terms of the RMW.
In about 3-4 minutes.
Okay. Oh, sorry. So yeah, I'm gonna probably quickly talk. We also collaborate with DTC to evaluate the cumulative scheme, comparing the GF scheme versus SAS scheme. We showed that the GF scheme did a little bit better job. So I think Catherine Newman is here, so she may talk more about this. I'll quickly talk about our wind gas model. So this is actually the project funded by HFIP. We want to thank Mark and I are the PIs. So this is one of our project products. So we try to put a real-time wind gas forecast through HAFS. This is one component by using this ECMWF wind gas parameterization. So we actually modify this ERA5 wind parameterization through tuning it against observation. So we have tested 10 cases in both HAFS A and HAFS B. So this is the gas factor as a function of wind speed. So the red color is the original, the default. The blue color is after our tuning, and then the black one are the observations. You see, our tuned wind gas match with observation pretty well. So just quickly, this is not updated slides. So I actually have slides showing the real time, like a 2D map of wind gas from HAFS B. So this just quickly show you observation. This is a Hurricane Ida. We also found something interesting. So I plotted the gas factor as a function of wind speed and radius, comparing this is onshore versus offshore. We found the offshore side always have stronger, larger gas factor. So this is we want to understand this and to see if our wind gas parameterization can reproduce this in HAFS. So this is my last slide. I put a good amount of questions. So for instance, can we combine the vertical and horizontal diffusion effects through a TKE, 3D TKE? So we have a JTDI on the project. Pingzhu and I. Pingzhu will talk about this. This is not the updated slides, but I have a question at the end, actually asking, can the existing and new observations answer these questions, and how can we answer these questions? Yeah, that's it. Thank you.
Thank you so much, June. All right, so we're going to continue the theme, moving on to our next talk from HRD. Joe, are you online?
Yeah, I'm here.
Awesome. All right, so we have Joe Sion talking to us next about emerging tech. So I'll pass it over to you, Joe.
Yeah, are you guys going to advance the slides, or that's what Aaron said? So just want to get on the same page, or I can.
Yes. We
Okay.
will.
Yeah, we will be, Joe. Just give us a second to get everything set up in the share to the remote.
Okay. Yes, let me know while you're setting that up. I guess I'll just give an intro. Yeah, I'm Joe Sion. I work at NOAA's HRD, and today we're going to talk a little bit about what you heard from Jin mention and Jason Sipple a little bit earlier about some of the emerging technology observations that we've had. In the past, it was really the emerging technologies we used were predominantly drones, different types of drones. We're in it's our third generation of drones now, if you go back to the early 00s. But we've expanded into other types of technology. So today we're going to talk.
You're good on your slides now.
Okay. All right. So I'll still keep on this slide right now. You know, we're still looking at drones, of course, and that's we deployed 19 drones this year, which I'll get into in a minute. But we also deployed the next generation drop sondes, which are called stream sondes. Ended up deploying over 91 of those. So we're moving into that, going into the future. I don't have too much to say right now, but this team here that we have listed is pretty diverse. I won't read into everyone there, but there's a big team, multiple line offices. We're at AOML, OAR, OMAO, Weather Service, and then universities, CMIS, of course, and CSU, Embry-Riddle as well, and then a couple of companies. You got Blackswift, Skyfora, Dragoon, and Strata Solutions. Today, we're going to highlight what we did with Blackswift and Skyfora, but you're going to hear more in the future of Dragoon, who makes a long duration UAS, and Strata Solutions, which will operate drones in the stratosphere. So that's kind of what's on the horizon, and I'm excited about it. And next slide, please. So today we're going to talk about, as I said, basically our drone operations, and just a summary. Won't get into the weeds here. It's sort of the view from 10,000 feet, or well, if you're a drone, view from a couple hundred feet. For the S0, the S0 is built by Blackswift. I'm out in Colorado, so the Blackswift team is also in Boulder, and they built from scratch. Essentially, we've been working with them since the early SBIR days. So this is a great example and success story of just starting really from nothing and coming out with, hey, what are our requirements, and build it. And we've basically started in 2018, and here we are 6 years later, probably close to transition within a year or so. So it's a great transition, SBIR story, research to operations, and really proud of this work. So with that intro, we ended up sampling 4 hurricanes this year with the S0. We had 19 flights, a little over 20 hours of flight time, a record flight, which was a Guinness. Guinness has reached out to us. So this is a Guinness record for 105 nautical miles. We also set Guinness record for max winds, maybe anywhere ever on this planet. A little bold, but I don't know about that for a drone. Unless DARPA is sampling hurricanes or tornadoes that we're unaware of, I think that actually is a record anywhere. Certainly a record for us. And then max range to P3, which to those not involved in the engineering may say like whatever, not whatever. Trust me, the Coyote days, we could communicate between the P3 and the drone about 10 miles. So this is 20-fold that. And that was probably the biggest engineering hurdle we had. And that's going to be the biggest hurdle cleared to get us to operations. Why? Because the range, because the legs of the P3 during operational missions is about 105 nautical miles. What it means is the P3 can do its business and doesn't have to babysit. So this was a huge and first time ever advantage. And I should also say that all these operations were in operational settings. So we had to operate in very much more strict environments, and it succeeded really well. Next slide, please. Aaron, can you go to the next slide? Okay, thank you. So as I said, we hit 4 hurricanes. We started in Ernesto. You can see where we were. And then we progressed basically into the Gulf after that with Francine, which is Cat 2 Ernesto was maxed out at. Francine was closer to the western portion of the Gulf, and was Cat 1. You can see the time frames, August, September. We progressed through much of the season. And we had S0 missions. Next slide, please. So you can see the different missions that we had, and this is the tracks superimposed with where we had the S0 missions, and you can see the different colors. So for example, Helene is in pink, at least from my screen. Hopefully it's the same. We can see that Ernesto was light blue, Francine was light green, and then Milton was sort of a burnt sienna orange. And in all, we got, it says 16 here. Actually, we revised that. It's, we think 17 of them are successful. And one of those that was not successful in Francine was, I have to put the blame on Noah for that. I'll take it personally. But we didn't really set that one up for success. We had some technical issues with the GPS receiver on that. So really, if you want to be technical, really 18 out of 19 successful drops. And that's really quite remarkable. So next slide, please. So this is the same sort of plot minus the tracks. And you can see this is, actually, this is Barilla's visualization of all the different pastas they have. So if you're interested in getting, you know, some of the curly cues, you can go there. Now, obviously, these are the tracks that we had. And the one that's right off Tampa there to the, that's the last flight in Helene. That's the first time we did a circumnavigation, a full circumnavigation in any drone. So as you can see, after that, we did more. But that was very interesting. And the storm was Cat 4 at the time. So it was a strong storm. We also measured, next slide, please. We also measured storms, category 5 winds, which I'll get into too. So we really kind of spread from category 1 to 5 over this season. So you can see here for Ernesto, we had 4 flights that we started off the season with a bang. Really, it was really perfect flights. The shortest flight I think we had in Ernesto was something about 55 to 58. Oh no, I'm sorry, it's right here. The duration was 66 minutes was the shortest we had. And you can see this, but this chart tells you what the max wind speeds were. And it tells you where those wind speeds were. And I'll mention that we are interested in working with our new proposals that we're going to have to try to reduce these. So it's one thing to say, hey, we're at, where are these winds at? How do we reduce them down to surface so they're of utmost value to the hurricane forecasters? We are working on that. Also impact studies with our HRD folks, and also we're looking for new funding to look at impact studies. So data denial and also impact on, you know, potentially what it could have had for storm surge models as well. So this plot, you're going to see them similar. So I'll explain this one. It's basically altitude and time on the top. And you can see which different, we had 4 missions. So the color coding gives you the mission. And on the bottom, it's the same plot, except we have wind speed there. So you can see where we had those strong wind speeds. You can see we measured right below 500 meters. We got over 70 knots. No, actually, yeah, about the max winds we got in total was about 130 knots. So you can see where that was by the color coding. Next slide, please. So similar for Francine, this is over in the western portion of the Gulf Stream. This Gulf of Mexico, and we can see about one flight that didn't work. Basically, it's we did get data though, so it's essentially a sophisticated sounding or sophisticated drops on. But for the most part, you can see our step descent technique, and we had 4 drops here. Not as strong as some of the storms that I'm going to go into here, but you can see some of the details. Next slide, please. Next slide, please. And in Helene, we measured, this is where I said we got our first circumnavigation. A lot of firsts here. We had 7, so this was our most amount of drones here that we covered. And we set one of our records here, I think flight 6 for the comms range. And you can see the different altitudes. I also want to say that we're flying at altitudes when we come down from 5,000 feet that we can get TDR comparisons. And we're in the process of doing that to help validate the winds and also to fill in spots where maybe TDR is not hitting. So you don't have areas of reflection, and it can do that as well. So we'll keep doing that in the future just to have some comparisons, but also maybe to fill in if needed. We're looking at AI to really give us different ways to sample more efficiently going forward. Next slide, please. So Milton was the strongest storm. We were in that, we were able to deploy when it was a 897 storm. It was Cat 5 at its peak. And you can see, and that's for flight number 1, where we had 209 knots. So that's another record that we set. Interestingly, that was at 500 meters where we saw that. So it'd be interesting to see how it compared with the TDR analyses that Guo is Guolin is working on. I just want to give another shout out. I should have done it earlier. Guo is our master developer of slides here too for the season summary. So thanks, Guo, specifically to you for helping put all these together. Yeah, so again, here you can see stronger winds, category 5, and you can see the differences. We did have one failure in S02 that the motor didn't turn on in that one. So again, though, even with that limited capability, we still will get some data, some turbulence data. So we're measuring pressure, temperature, winds, and we have a multi-hole probe on here too. So we're getting turbulence data and vertical velocity. Next slide, please.
We have about 5 minutes, Joe.
Sure. Yeah, I'm getting close. So I'm going to talk a little bit about stream song, and then I'll be done. So this just is a breakdown of where we flew. So we had 3 S0s in category 5 conditions, 2 in category 4, and so on and so on. You can see the breakdown. So this is nice when building our statistics. I think we really want to show where the observations are coming from. Next slide, please. One slide that I want to have here, and I should have put it on here. I'll get it on the next before I get into this. It's an interesting plot that shows altitude with wind speed, and you can really see where we are. And we're essentially most of the time below 500 meters, and there's a lot of metadata there too. So it's like not only just altitude with wind speed, but we can break it down with what quadrant we're in, where we are. So I think that's going to really help us with regard to making the products that we're sending. This data is being sent from the P3, from the UAS to the P3 in real time to the Hurricane Center, where Mark DeMaria and his team, CIRA team, are putting that into AWIPS Cloud right now. We'd hope to graduate from AWIPS Cloud into AWIPS this year. We'll talking with folks about that, and allowing that data to be used in real time. It is now, but just to get it into AWIPS operational, I guess. And different products to reduce those levels, like we've done for decades with flight level, to have those HD obs that are coming in from the drones to be representative, use that information to give us what the 10-meter wind is, let's say. And then that information can be used for forecast, but also for storm surge, maybe initialization, and then ultimately to be integrated into the numerical models down the road. So I wanted to get that in. So with that, I would say just a couple of comments. We flew in Hurricane Beryl. And that was very interesting. We had 16 stream sondes. These are 15 gram versus 8 ounce. The mini sondes are 8 ounces. These are 15 grams, so half an ounce. So we have the ability to swarm with them, and they're very, very lightweight. Pressure, temperature, wind, humidity. And according to the manufacturer, we have to prove it still better winds, about 20% better winds, because we're using a different constellation than is used for the typical drop sondes. So for Beryl, we had 16 total, 4 in each eye wall with the drops on there. So really 5 in each quadrant of the eye wall. We're analyzing that. That should be very interesting to do to help with validation of this new technology. We also had some on the following day. Next, and thank you to June for really making that happen. So this is a couple slides here. This is on the left. You've got winds in blue, vertical winds in red, and then the wind direction in green. And on the right, you can see sort of that's a lat long, so you can see how it curves around as it's deployed. And in this case, we got 104 meters per second. We operated Beryl. These are from Beryl, so we're in Cat 5 eye wall conditions here. Next slide, please. Similar, 105. This is 4 minutes later. So as I said, we dropped 4 per eye wall. So this is one sequence where we just dropped very quickly. We can drop them even faster than we can drop them in tens of seconds now with the swarm version. So that'll be something we show later. Next slide, please. Interesting here, you can see the updraft on the side. Can you go to the next slide? I think it's a little bit better. No, actually go back 2 if you can. Oh, sorry, one more, back. Okay, so you can see on the right that we're getting these updrafts, and they're so light that they actually go up. So in this case, for 400 meters after it was deployed, Sim Averson has done a good job showing up sondes, and we're going to have a lot of up stream sondes because they're so light. So that's something that's an interesting characteristic. They stay aloft longer, and their fall speed is about half of a drop sonde. So that's something to keep in mind as well. Next slide, next 2 slides actually. Yeah. And then, yeah, so you can just see the variation in data. Next slide. Okay, so this is where we had the 900 meter updraft that recorded the a device going up 900 meters before it eventually came back down again. So very interesting. We'll have to figure out how to interpret this. We had an ascent rate about 4.2 meters per second, which is pretty remarkable. Again, these are very, very turbulent category 5 barrel eye wall drops. Next slide, please. So basically post barrel, that was not doing swarm capability. In Raphael, we were able to do swarming. We dropped 20 at once, very quickly, seconds apart, a few seconds at a time. We're analyzing that data. So the SDR system allows us now to drop up to 50 at once if we want to. It's expensive, so we're not going to be dropping 50. The cost of these is roughly about 500 per. So it's still cheaper than the drop zone, but still expensive. So we're not going to just throw them out like candy, but we can. So it's a nice addition. We're still in the validation part of this. We plan to hopefully send this data in real time along with the S0 data that we have next year. And this is really an exciting development. As you can see, the line of sight is about 1,000 kilometers. So we really, and we're on 42 and 43 too. So along with the S0, I should say, on both planes, that was another thing that we did for the first time this year. Okay, that's it. Thank you.
Thanks so much, Joe. I really appreciate you letting us know about the latest on the small UAS as well as the streamsons. So with that, we've heard a lot about individual instruments as well as the field program. So we're going to switch gears and move into the aircraft. So as we all know, P3s are going to be retired in the coming years. So we invited Jerry Foreman and Commander Rob Mitchell to come speak with us today about the upcoming C-130s. So Commander Mitchell, are you online?
Good morning. Can you hear me?
Yes, you're a little bit low. Did you try again?
I think I'm the only one in the room, so let me move the speaker. Is this any better?
Can you guys all hear?
If not, let me try this.
Okay, it's a little better, so maybe
Just bear with us for a second here. We're also trying to get your slides on the screen in-house. We've got them online. No, there's no.
Better for this time.
Yeah, just you did the remote games. No, but I know that I've seen stuff on the screen. Sorry, we had. What's that? Yeah,
all right. We should be all good to go.
Sorry,
So
we had a PowerPoint overriding the other one.
Oh, okay. Over to you, Commander Mitchell. It's all yours.
All right. Thank you, everybody. And good morning. Appreciate the opportunity to present to you guys. As was mentioned, our goal here is to talk about the P3 replacement, which is going to be our C-130J aircraft. I'm Commander Rob Mitchell. For those that don't know me, I am a P3 Hurricane aircraft commander and am currently acting as the C-130 program manager. So I'll be in charge of getting the program started and talking about the designs of the modifications to the aircraft to be able to support the amazing research that you guys are doing. Mr. Jerry Foreman is the Deputy Director for Aircraft Acquisition, so he's my boss, and he's in charge of all of aircraft acquisition, so including the P3 to C-130 transition, the G4 to G550 transition, and any future light aircraft. On the team, we also have Mr. Jeff Hartberger as our lead acquisitions engineer. And then Mr. Alan Goldstein is the G550 program manager and overall instrumentation guru on the aircraft as well. So for the room, I don't know if I need to verbalize, but next slide. So the P3 replacement's been going on for a while. This is just a quick overview, and you guys can take a look at it in the slide deck that's provided. But as an overview, we started in 2015. Looking at a economic impact study and developing an analysis of alternatives. That narrowed down the scope of potential airframes that can fly through hurricanes. That was updated in 2020 to 2021 with impact or feedback from the research community to further narrow the scope of potential airframes and the impact of fleet size and capabilities that we need to incorporate into the aircraft. That went into a request for information for a tail Doppler radar replacement. We'll talk about that a little bit later as far as how we're going to incorporate that technology onto the airframe. Ultimately, that went into our aircraft plan that was approved by Congress in 2022. That led to congressional funding being provided in December of 2023. December of 22 in FY23, which really allowed us to kick off the program. So we identified the C-130 as the only applicable airframe, which allowed us to get on contract in October of 2023 to preserve our production slot and make sure that we get the aircraft by 2030 when we need to retire the P3s. We sent out a request for proposal, and ultimately in September of 2024, we awarded the production and modification contract to Lockheed Martin, who's going to be building and designing the mission modifications into the aircraft. Next slide. So with that award, and thanks to the pre-production contract that we awarded last year, this is our estimated program schedule. And so without going into all the details, we're concurrently going through a VSDR, which is what we're calling the tail Doppler radar. It's a vertically scanning Doppler radar. We're currently going through an analysis of alternatives. I have the engineering team from Lockheed Martin at the Aircraft Operations Center today. So we're talking about capabilities and requirements. And then we're going to be designing the modifications for the missionization, which we'll talk about. While we're doing that, the production of the aircraft is starting. And we expect the production aircraft to be complete at the end of FY27, early FY28. And then we're going to go straight into a missionization phase with Lockheed Martin or potentially another vendor. As of now, they're predicting a 12-month missionization phase. So AOC should have an aircraft around the middle of fiscal year 2029. It gives us about a year to integrate the aircraft with the instrumentation here at AOC, start doing some intercomparison test flights, and be able to replace the minimum capabilities of the P3 by through the FY30 hurricane season, and be able to retire the P3s by the end of FY2030. Next slide. So for our acquisition program, as I kind of laid out on the schedule, we really have three phases. We have the production phase, we have the missionization modification phase, which again is installing the provisions for the aircraft, and then we have the integration phase, which is going to be conducted at the Aircraft Operations Center, bringing in the instrumentation from the science community and incorporating that onto the aircraft. So for everybody on the phone call here, I'm going to back up one slide to the estimated program schedule. We're looking at mid FY29 is when we are preparing to have the integration of instrumentation on the aircraft. So for any sort of new gizmos that you're thinking about, 2029 should be the kind of time frame that you need to have some specs and some details to be able to provide AOC to start the engineering to integrate onto the aircraft. So moving forward, for the room, I'm on the VSDR slide, so it's 2 slides forward from what I was. So tail Doppler radar, that we understand is a critical instrument for a lot of the research and the 3-dimensional wind fields that you guys are now analyzing as we go through the storm. The challenge that we all have is that the C-130 doesn't have a tail that's capable of incorporating the current tail Doppler radar. So what we're currently doing is a vertically scanning Doppler radar analysis of alternatives. What that is we have a representative from the Oklahoma University Advanced Radar Research Center is consulting with Lockheed Martin, and they're going to kind of query the entirety of industry, both research, government, and commercial, to figure out what kind of radar technologies can provide the detail and the capabilities of the tail Doppler radar, what kind of form factor that may be. We all know that there's an NSF-funded program for APAR, which has phased array radars positioned around the C-130. But we also know that that program is probably not going to be capable of having an operational instrument by 2030. So we're evaluating whether it's pod-mounted solutions, fuselage-mounted solutions. We're open to anything. So we expect that analysis of alternatives to be complete by June of 2025, at which point NOAA as a whole, both OMAO, OAR, NWS, all the line offices are going to have feedback into what solution we pursue moving forward. So that's our nearest term development. Flight station characteristics. The big thing on the next slide is that the flight director and one other person are likely to be on the aircraft flight deck as opposed to on the cargo deck. So that's going to increase crew coordination, hopefully increase safety, and allow us to, continue to coordinate and safely fly into the storms. I have some of the specs of the aircraft listed there just for reference for you guys in the future. The one things to highlight, the survey speed for the C-130 is a little bit slower, about 180 knots compared to a 210. And then we are working with Lockheed Martin to try to incorporate a more advanced nose weather radar. So the RDR 4000 has 3D volumetric scans that we're hoping to be able to provide to the flight directors and the science community. And so there's some production modifications to the aircraft that we're working through. I'm sensitive of the time, so I'll be available for the discussions afterwards. But the next slide is the mission layout. The big goal is that we have provisions for 16 stations in the aircraft. So that's more than what the P3 has in the sense of being able to host research opportunities. Because the flight directors are now going to be on the flight deck, we're likely to have the remote launched AVAP system and trying to automate some of the systems. We may not have to have a AVAPS operator per se. And so that allows us to host all these stations with researchers. To the comment that I did see, we're working on worldwide capable avionics, enhanced nose weather radar. We are going to have a lower fuselage radar, and we are having dual high-speed internet. So it's a KU-KA band system that is going to allow some remote operations. And our minimum is a 3 megabyte per second requirement. And we hope to achieve more than that. So that's about a 10-fold increase of what we can do currently. And so how we use that in the future will be something that we can work with. So I have room for like 3 more minutes. I apologize, guys. The current design efforts that we're working with, just for your awareness going through, we do have an APY-11, the same lower fuselage radar that we have on the P3. There will be a shadowing from the aircraft, so the aft quadrant will be a little bit different. So we're talking with flight directors, trying to see if we can fix that. Sorry for the room. I'm 2 slides forward. Okay, you guys have a static image, so I apologize. I have some stacked slides here. But we'll keep working through. We do have upper and lower aperture ports that we're going to have to incorporate instruments similar to the P3s. We're trying to maintain centerline, both lower and upper. We are working on missionized hardpoints. So we'll have a third hardpoint, which is new for the aircraft on the outer wing, and then a wingtip hardpoint, which will be able to incorporate our cloud physics probes and any sort of outer instrumentation sampling. So that's something that we're working on. And then lastly, a pressurized launch tube to be able to incorporate the A-size buoys and also allow in-flight reloading and expendables larger than the A-size. So we're working with the C-130 community, the Air Force, the NCAR, Coast Guard, DHS, as we're building out this aircraft, and hope to be able to provide a sustainable research platform that can try and duplicate what the P3 does, but also be sustainable and flexible for the future. So with that, I'm going to go off camera and move rooms because I think there's an overlapping meeting, but I'll be available for the questioning at the end.
Thanks so much, Commander Mitchell. We are actually at the end of our session. We were going to begin the Q&A for about 15 minutes. If you could stick around. Hopefully.
You say you had to change rooms. There's people.
Oh, okay. All right, so.
Side conversation is sort of having one.
Oh, okay. I got it. All right. So with that, I just want to thank all of our speakers. This was a long session. So thank you to all of you for presenting very early this morning. And if you have any questions for any of them, please raise your hand and put them in the chat online.
There was a question from
Maria.
Rob.
Yeah, this is Maria from EMC. So they have a great presentation. Thank you. So I just wanted to ask you about the progress of calculating directly the momentum fluxes from sail drawings.
I'm going to pass it to the person sitting next to me who is the one doing just that work to give an update, Greg.
Okay, so what's the question specifically? So how we calculate them, what the progress is? Okay, so we have made progress. We've been doing quality control on the 20 hertz data, which is not always easy. And I think we've gotten to a good point where we have almost a finalized 20 hertz wind, 3D wind data set over 3 years now, 2021 through 2023. We have I don't remember exactly, 15 different hurricane intercepts where we have data. And we've calculated the momentum fluxes and the drag coefficient for all of them. And it looks good. I don't know. I mean, I don't know how much detail you want, I guess, on the results, but we do have good results now from 3 years.
No, that's excellent. Looking forward to the results to compare with the CD that is being used.
Yeah, exactly. Yeah. I'll give a presentation. I'll probably show some results at Fall AGU. If you'll be at Fall AGU in December, I'm probably gonna. We'll show results coming up at meetings in the future. More details.
We can probably work you into an HFIP monthly seminar in the spring as well, if you'd like.
Okay. Yeah.
I can also quickly share my screen and just show the slide. It was a backup slide if that's easier or preferred.
Maybe that could be done offline just
Okay.
because of how short our Q&A session is.
Perfect.
So I'm going to move to, we have 2 questions in the chat online for Commander Mitchell. Are you online, Rob? Can you see those questions?
I am still here.
I can read out the first one. This is from Pete Black. He asked if the new 130s will have a 6-bladed prop like the current in-car C-130.
They will. So the NCAR actually has the NP2000, which I think is an 8-bladed prop. We will have the WC-130 6-bladed props. So it's the standard prop with a minor modification to improve the weather capabilities. And then
a question to Jun's talk. So yeah, first, thank you for bringing about like TCPBL, the modification in the HAFS being used right now. So yeah, so based on the discussion there's something I want to add is the evaluation from that paper. Yeah, we're using 1 year, 2021. So some of that we find the track was a little bit degraded, but later on, so Annie Hazelton, so in the last year, so published another paper discussed the Thompson and TCPBL impact on the TC forecast, and we did not find a very significant difference between the track performance. So basically, they have more cases. They have 3 times than the paper I published in 2022. So and later on, and also about the structure part. So the TCPBL basically they improve the inner core size. So that's the main takeaway from that slides as well. So you see the inflow angle was picked closer to the eye. So that's the main reason. Like they can perform pretty well for the rapid intensification forecast. Like especially this season, like you see the Milton as well. Yeah. So this is basically something we are trying to do, and carry on. We are doing the unifying the mass fluxes for the PBO and shallow cumulus scheme. So hopefully that can further impact the especially the outer core size. So that's the goal we should try to work on. Yeah. Thanks.
Thanks, Xiaomin, for the updates. Yeah, looking forward to your new result for modifying the cumulus part scheme. Yeah, thank you.
Let's move to Joe online for his question.
Yeah, it's more of a comment. The question about the turbulent fluxes, I guess momentum fluxes specifically. Just want to reiterate particularly from the S0 drones that we have a multi-hole probe on there. I guess sort of accentuated that more. So we're able to get direct fluxes, momentum for sure, and we also believe enthalpy flux too eventually. Right now we're getting about 5 hertz data on average getting sent back to us, but that is because we're still in the early stage of getting a lot of engineering data back to make sure that things are working great. Remember, this is our first big year, but going forward, 10 hertz is absolutely possible. And then, I don't want to promise this, but the manufacturer is saying, we can push up to about 20 hertz. So this is something to think about going forward as far as it's not just PTH, and also sea surface temperature, because we have an IR sensor that looks down. We're going to be getting that as well, maybe some wave information. But yeah, for fluxes, it's cell drones, definitely a great source, but it's also what we're doing as well should be able to provide that.
Thanks, Joe.
Gopal, can you hold up? Shujin was next. Thank you. And then Hyun Suk will be after Gopal.
So I have 2 questions. One is for Joe Sion. So you are testing all those emerging technology, and what extra resource you need to study the impact of this emerging technology. Then the second question is for LC. Rob, you're going to answer this question. So is there any capability to study the microphysics in the convection regime? So right now we are limited to certain area we can't fly. I wish we have those kind of capability in the future with the C-130. Thank you.
So to answer your question, Sujin, well, first we've had a great season, but first thing we have to do is restock. And we don't have any right now. This minute, we do not have any S0s. So we need to do that. We plan on testing in June to do some other things, and then of course we plan on flying next year. So we have some proposals in, and we've talked with UXS Captain Mowat. So I'm comfortable that we're gonna work on that, and we're gonna get that. That's the first thing. The other thing too, I would say, is as I mentioned, we're expanding into different technology. We're looking at a long duration UAS. We're looking at having drones that can potentially drop other drones or stream sondes from the stratosphere above the storm and kind of stay and monitor the storm like a very poor person's global hawk. So that's on the horizon. But I would say to specifically answer your question of like what we're doing now from a science standpoint, data impact, and more data impacts. Let's show what these data, how these data make an impact on the near-term forecast, what the forecasters do, what the modeling aspects are, how these can potentially impact something like storm surge by giving us a different initial storm structure and what the max winds are. So that is really what we want to do, and I'm leaning on our science team, our very good science team, to help do that. And then going down the road, I think data assimilation and model improvement through physics evaluation is stuff that Jen has been leading for a long time. That's next. And then eventually getting this data into models, and AI too. We want to really leverage artificial intelligence, machine learning as one example. Hey, where should we sample? Not just we say, okay, let's go on the owl. Let's use AI to tell us the optimal sampling strategies. And also we can use AI to have the drone fly better and give us 10, 15 more minutes of flight. We're also looking at engineering battery changes to get us more duration. Everything's lithium ion, but that doesn't mean that's the future. There are different chemistries that can really enhance what we're doing, and we're looking at that as well. I know it's a long answer, but we're doing a lot of things.
Thanks, Joe. We're going to go to this next question in the chat. Philippe, are you here? Or are you online right now? If you're online, would you mind?
Hey, I'm actually online currently right now, but I had a question for Zorana. Very extensive and impressive presentation you presented earlier, but I just kind of had a larger scale question with all these issues that you've uncovered with the SFMR instrumentation on board the NOAA P3. where are resources better served? Are we still going to try to account for all these issues and fix some of the SFMR issues that have been uncovered with the sensor for calibration? Or are we better served to trying to shift towards maybe a newer data set or newer instrument that may not have such issues?
Well, I would say it's both, because we have 20 years of most extreme wind measurements just from SFMR. We cannot lose that. We definitely should go to future with something new based on the lessons we learned so far. But that's not going to happen for next season. You will still have several seasons at least where SFMR will be coming in, right? If nothing else from Air Force, so it would be good to address that as soon as possible. But the point I want to make here is that no matter which instrument, we cannot forget about validation of the data. We constantly have to validate. That's in second-hand kind of thing done. We get these new products. They all show kind of great measurements, but we don't really know errors in them. Let's not repeat the SFMR.
Thanks.
Thanks, Yorana. And I want to apologize. I cut Julian's questions off. So if you want to reiterate your second question.
Yeah, there's a second question. I think this is for Rob. When the current P3 have the cloud physics instrument on that, but we limit to fly only the stratiform cloud regime. With this new C-130, I hope can we build this much more strong flight, can go into those convection regime, especially we need those ice data to improve our microphysics processes. That is probably, there's totally different kind of situation we have, but right now we just don't have enough data to get our modeling side, get the verification or get the data to improve that. Sorry.
Yeah, so two things. The first is, I'll be honest with you as an operator, I don't know if you're ever going to get somebody, a crewed aircraft at least, that can fly in convective iced areas of a storm. I mean, that's what the South Dakota School of Mines instrumented, what is it, T6 or something used to do. That's what the NSF effort to get an A-10 to do that type of work. That's going to be tough. T-28, thank you. That being said, the C-130s do have significantly greater altitude performance than the P3s do. The P3s, for many of you that have operated on it, suffers in icing conditions at high altitude. The engines that we have a greater than standard loss of power. That is not the case with the C-130s. And so depending on the weights of the aircraft, the numbers that I put forward in the presentation, which you guys should have access to, I think had a maximum altitude of 32,000 feet. That's relatively conservative based on a unknown gross weight and unknown drag count. But I anticipate from a mission perspective, much like the 53rd does for atmospheric rivers, we should be able to fly comfortably in degraded conditions in the high 20s to low 30s in altitude. Now, that being said, again, I think in ice, in convection at high altitudes, I don't think a crewed aircraft is going to get you there.
Thanks, Rob. All right, we're going to do one more question. Oh, okay. GoPro graciously gave up his spot in line for one more question.
Just try to keep it relatively short because we're already into the break time. Thank you.
My question, this is Hyun-Suk Kim from AOML. Question to Zorana. And we, EMC and I, were considering building up the three-way coupling by means adding wave coupling. And as you know, as you heard, Celadon observed wave height more than 10 meter. Right? So that means the 10-meter wind throughout the concept, usually is, some question to regarding the IRAP, how, what is the lowest altitude you can convince the data is good, trust?
So basically, we are retrieving with Doppler winds every 30 meters. So the lowest one we would get is a 30-meter wind, and then that needs to be reduced to 10 meters, right, to compare. So how that is done, that's another story, right? But we are reducing it now the way it's known so far, but we are looking into how to reduce it. In no rain conditions, we are retrieving using the scatterometry, and scatterometry geophysical model function is tuned to 10-meter wind. But that's tuned, it's not like you are measuring, right? You are measuring average over the certain area signal that is coming on. And there will be some modifications due to high waves, but you cannot take that 10 meters as it's cutting into the waves. That's a GMF that is tuned to 10-meter winds. So
Right.
those are two different things. Yeah.
Yes. So, okay. So 30 meters. you can-
That's from
so that is
Doppler.
good.
Yeah. From
Okay.
scatterometry, everything is tuned to 10-meter wind.
Yeah.
Yeah.
Okay. But the reason you cut off at the 30 meters is because of the sea conditions or just instrument attenuation, sound, whatever?
No, well, because you are measuring with different incidence angles, you will be going down the surface, right, with the slant range. So we have to stop at 30.
Thank you. We have to unfortunately cut off the Q&A. We've already eaten into the break. We've got about 10 minutes for break, and we need to load the slides for the next session. So apologies for those of you that had hands up or questions, if you would be able to take them offline with the presenters that you would like to ask. Or if you do have one you wanted to ask, put it in the chat and we will capture it. For those of you in the room, if you commuted here, please bring your parking tickets to Jason standing back by the door in the blue shirt, waving his hand. I'm going to take them up to get them validated very soon.